Hello everyone, this is Professor Roman. Let's continue the ring theory lectures. It's now time that we took a look at quotient rings. We have seen that ideals, being the kernels of ring maps, are the analog of normal subgroups. So we can now consider how ideals are used to define quotient rings. So let R be a ring and let I be an ideal of R. The equivalence relation known as congruence modulo I is defined, this is the symbol A congruent to B mod I, if the difference A minus B belongs to the ideal. This is an equivalence relation, which I'll let you confirm, and it therefore induces a partition on R whose blocks are referred to as congruence classes. I'll explain the term congruence in a few minutes. These congruence classes are, in fact, the sets little a plus I, which consist of the sums little a plus little I as I ranges over the ideal. And this is called a coset of I, something you should be familiar with from your studies of vector spaces and groups. A is a coset representative for this coset. So the distinct cosets of I form a partition of R, and we denote that by R mod I. This would be read R mod I. It's the set of all cosets of I in R. Now, equivalence modulo I, or congruence modulo I, is more than just an equivalence relation. It's more than just being reflexive, symmetric, and transitive, because it preserves the binary and unary operations in the ring. So if A is equivalent to B, or congruent mod I to B, and C and D are congruent, then A plus C is congruent to B plus D, and AC is congruent to BD. This is the preservation of addition and multiplication. And here is the preservation of negatives. This is the unary ring operation. Speaking in general terms, an equivalence relation on an algebraic structure, such as a vector space, a group, or a ring, that preserves the algebraic structure is called a congruence relation. These are extremely important types of equivalence relations in algebra. So that accounts for the term congruence mod I and congruence class, because we have a congruence relation. And because congruence mod I is a congruence relation, because it preserves the ring operations, we can raise the ring structure from R to R mod I, or lower it, depending on your point of view. So I'm leaving proof of the following for you. If R is a ring and I is an ideal of R, then the set R mod I is a ring under the well-defined, and that's something that needs to be checked, coset addition and multiplication. Under these operations, R mod I is called the quotient ring of R modulo I. In the case of vector spaces and groups and rings, one can simply define quotient structures directly and really never need to mention the fact that one is dealing with a congruence relation. I think it's quite typical just to use the congruence relation properties without actually calling it a congruence relation. In the case of vector spaces, you just can take any subspace and factor by it, take the cosets, define coset addition and scalar multiplication. In the case of groups, you can take normal subgroups, form their cosets, and define the define the coset product. In the case of rings, you can do something similar. You can take an ideal, consider the collection of cosets of that ideal, define addition and multiplication, show they're well defined, and show that you have a ring. But what's interesting about this situation is that there's one algebraic structure where that doesn't work. In the three cases I just elaborated, there are special types of substructures that you can factor by. Now, in the case of vector spaces, any subspace will do. In the case of groups, you need a normal subgroup. In the case of rings, you need an ideal. But in lattice theory, in general lattice theory, there is no such substructure. And the only way in general to factor a lattice is with a congruence relation. So if L is a lattice and theta is a congruence relation on L, then we can define L mod theta and show that it's a lattice. There's no special substructure of lattices that will play the role of subspace, normal subgroup, or ideal. So if we want to speak in the most general possible terms, factorization is done by a congruence relation on the structure. And that's the real story. But then in most cases, but not all, there's a way to get around dealing with the congruence relation directly by defining special substructures, normal subgroups, ideals. So now you have the full picture. Consider now a pair of ideals I and j, for which I is contained in j. Then as sets, we can look at the set of cosets, the coset family. So this j mod I, so this would be all the cosets of I whose coset representatives come from the bigger ideal j. And this is a subset then of R mod I. Moreover, since j is an ideal of R, the set j mod I is closed under subtraction and multiplication by any element of R mod I. And here's what that looks like. And so j mod I is in fact an ideal of R mod I. So here's the theorem. Let R be a ring. Then if I and j are ideals, I contained in j, then j mod I is an ideal of R mod I. This is what you would hope for, what you would expect, but it does need attention. To describe the elements of this quotient ring, for example, this is the z square bracket x, the integer polynomials, factored out by this polynomial. Let I be the ideal, factored out by this ideal, this principal ideal. So let I be this ideal. Now we can always write any polynomial in this form by division. This is the division algorithm. Q of x times this polynomial plus r of x. R of x is the remainder. Its degree is less than or equal to 1. And that would include r of x equals 0, because I hope I said sometime, if not I'm saying it now, we'll set the degree of the 0 polynomial as negative infinity. And this is probably why we want to do that. Not everybody does. So this is an arbitrary polynomial. This is the coset of that polynomial. It looks like this. And since this is a multiple of the generator of the ideal of I, this reduces to r. This reduces to r of x plus I. This is 0. This is the 0 coset. It's I. So, put succinctly, p of x plus I, this coset, is the same as p of x bar plus I, where p of x bar is the residue of p of x mod this quadratic polynomial. And so, since we're factoring by this quadratic, p of x bar is at most linear. So this quotient ring is this set of linear polynomial plus I. And one should show that these are all in fact distinct, and that's what I've done here. So that is the quotient ring. Here's another example. Consider the polynomial ring Z2 square bracket x. So now we're dealing with polynomials over Z2. So these have coefficients either equal to 0 or 1, which means the elements of this ring are essentially just sums of powers of x. So let's examine this quotient ring. If p of x is an element from the ring, we can again divide p of x by this polynomial, get a remainder that is at most linear. So if I is this ideal, then the quotient ring has, in this case, only 4 cosets, 4 elements. I, which is the 0 element, 1 plus I, which is the multiplicative identity, x plus I, and x plus 1 plus I. And these are distinct. So we have talked about ideals at some length, and we've defined quotient rings. We're now going to take a look at some special types of ideals. Coprime ideals coming next, maximal ideals, and prime ideals. So the rest of this chapter is devoted to a closer look at ideals. Since rings are generalization of the prototype ring of integers, it shouldn't come as a surprise that several properties of the integers have analogs for more general rings. And we've already seen this when we discussed divisibility, which does exist for all commutative rings. But we should also expect that the generalization of some properties of the integers to arbitrary rings, even commutative rings, may exhibit some, let's say, more erratic behavior, more unusual behavior, certainly a different behavior than it does for the integers. And also, we should expect that there's perhaps more than one way to generalize a property from the integers to more general rings. Bezos' identity for integers is something we've used quite often throughout these courses. It says that if two integers a and b are relatively prime, also called coprime, then that holds if and only if there exist integers r and s, for which ra plus sb equals 1. One direction's trivial. if this equation holds, then A and B are relatively prime. It's the other direction that's really the meat of Bezos' identity. This can be written in terms of ideals, principal ideals in the ring of integers. The ideal generated by A plus the ideal generated by B is the entire, Z. Okay. So this motivates a definition to generalize to arbitrary commutative rings. Two ideals I and J of R are coprime if their sum is the entire ring. Coprime ideals are also called co-maximal, but I'm going to shy away from that term. There's no point really in having two different terms for the same concept, at least not within the same book. It just adds to confusion. So we'll use the term coprime. Just be aware that other authors may use the term co-maximal. Ideals I and J are coprime if and only if there exists an element little I from I and little j from j, and for which the sum I plus j is 1. And you can verify that. In particular, the principal ideals, now we're dealing with an arbitrary commutative ring, the principal ideals generated by A and B are coprime if and only if there exists elements R and S in the ring for which this equation holds. Ra plus Sb equals 1. So the direct generalization of coprime integers is that of coprime principal ideals. But we're not limiting the term coprime to principal ideals. It applies to any pair of ideals whose sum is the whole ring. Summary: in a commutative ring R, the following are equivalent for elements A and B. The principal ideals are coprime. Bezos' identity holds in the ring. And when these conditions hold, we can say that the elements A and B are coprime, or relatively prime. So A and B are relatively prime or coprime if and only if, by definition, their principal ideals are coprime. For any ideals I and J in a commutative ring R, we have the product Ij is contained in the intersection. This just follows from the superclosure property of ideals. If I and J are coprime, then the reverse inclusion actually holds, because we know that there are elements little I and little j in their respective ideals whose sum is 1. And so if x is in the intersection, then x can be written as x times 1, which is x times I plus j, distributive law, xi plus xj. Now xi belongs to this ideal, this product. So does xj, therefore so does the sum, because this is an ideal. And so for coprime ideals, we have equality. The product is just the intersection. And this extends rather easily to more than two ideals, just using an inductive argument. So that looks like this. If I1 through In are pairwise coprime ideals, then their product is equal to their intersection. What this means is, because the intersection has the property that we can reorder the ideals any way we want, the same thing is true of the product. So for two ideals, it looks like Ij equals Ji. And this is news. You can't do this in general. but you can do it for coprime ideals or pairwise coprime ideals. Here's a fact that will be useful to us later. In fact, I inserted this late in the book because I realized I needed it later. So, the ideals I1 through In are pairwise coprime in R, if and only if, for all indices k between 1 and n. These two ideals are coprime. This is I not k, which is the product of all the ideals except ik, and this is ik. This is almost a lemma, really, a result we're going to need later, and that's why it's here. And here is the proof. You can see it's a bit long. We'll fix a value of k in this range. If I not k and ik are coprime, then since if j is different from k, then I sub not k is contained in I sub j. In other words, I sub not k is contained in all the ideals except ik. This ideal is contained in it's a product. It's contained in every one of the individual factors. We have R equals I not k plus ik, which is contained in ij plus ik, which is contained in R. And so we have equality here. And so ij plus ik is actually equal to R, and so these are coprime. Conversely, suppose that I1 through In are pairwise coprime. Then for each j different from k, the coprimeness of ij and ik give us this. Their sum is equal to the ring. Now we can take the product of these equations and use the distributive law. So R is the product as j ranges over all the indices except k of this sum, and that will look like this, where this is the product of all of the ideals except ik. So it's I sub not k. And this is all the terms involving I sub k in this product. The only one that does not comes from this first factor, for this first term here, I sub j. So as you take this product, you're going to have I sub k's in most of the terms. And so I can factor out the I sub k using the distributive law, and there'll be some other sum here. It'll be an ideal, j. So that looks like this. And that is contained in I sub not k plus I sub k, which is contained in R. So again, we have equality here in these inclusions. And so I sub not k and I sub k are coprime. Another way to justify this converse is going down to the element level. And I'm going to let you think about how you might do that to avoid the arithmetic of ideals, if you're so inclined. Okay? So that's the story on coprime ideals. Okay? The sum is equal to the entire ring, and we know that for coprime ideals the product is the intersection, and so the product becomes commutative, and this is a result we're going to need later in the course. Now let's talk about maximal and and prime ideals. And I'm going to assume all rings are commutative. I'll try to say commutative ring whenever I mention the word ring, but if I forget, I'm covered by this statement here. In this section, all rings are commutative. Okay. There are two very special types of ideals in a ring, individual ideals. Maximal ideals and prime ideals. And to understand the motivation behind the study of these ideals, their definition and study, if I is an ideal in a commutative ring R, then the factor ring, R mod I, may possess some additional properties that are not possessed by the parent ring, R. For example, R mod I might be an integral domain, even if R is not. R mod I might be a field, even if R is not. Well, as we're going to see, R mod I is an integral domain if and only if I is a so-called prime ideal. We'll define that. And R mod I is a field if and only if I is a maximal ideal, and I'll give you the definition of that as well. So that makes it fairly clear that maximal and prime ideals are important. And there are other reasons why they're important as well. Let's take a look at the field case first, when R mod I is a field. Suppose that R is a non-zero commutative ring and I is a proper ideal, and R mod I is a field. What can we learn about I? Well, if we take an element little a in the ring that's not in the ideal, then the coset A plus I belonging to the field R mod I has an inverse. So there's an element B for which AB plus I, which is the product, is equal to 1 plus I, the identity. Now, the ideal generated by I and A, so A is not in I, will contain the element AB, because it contains every multiple of A. And this equation then tells us that AB minus 1, which is in I, belongs to this ideal generated by I and A. So AB minus 1 belongs to this bigger ideal. AB belongs to this bigger ideal. Therefore 1 does, and so this ideal is in fact the entire ring. So what have we shown? If we take any element A that's not in the ideal, and we look at the ideal generated by I and that element, we get the whole ring. That tells us that any ideal of R that properly contains I will, because it must contain an ideal of this form, will be R. Okay. Any ideal that properly contains I must be the whole ring. So the only ideal that properly contains I is the ring itself. So this motivates the definition of maximal ideal. A proper ideal I in a ring R is a maximal ideal if I is maximal in the partially ordered set, I've written it this way, of all proper ideals of R. Not all ideals, but all proper ideals. So this is how you can express that in symbols. I is maximal if I is not equal to R, and whenever J properly contains I, J must be all of R. This notation, ideals sub not equal to R of R, is a little awkward. I'm not crazy about it, but I'm not aware of a good notation for the family of proper ideals of R. So it'll do. We're not going to use it very often. So what we have learned is that if the quotient ring is a field, then I is a maximal ideal of R. Conversely, if I is a maximal ideal of a non-zero, this should be commutative ring. I said it, all the rings are commutative, but I'm going to add that here anyway. Then R mod I will be a field, because if we have a non-identity element, non-zero element, A plus I, in the quotient, so A is not an I, so this ideal, generated by I and A, being a proper superset of I, must be R. So there's a little I in I and a little r in R, for which 1 equals I plus RA. That's what these elements look like. They have this form. And so the product, A plus I, R plus I, will be the identity. And so A plus I is invertible. Every non-zero element is invertible. We have a field. So here's the summary. Let R be a non-zero commutative ring. Then the quotient ring, R mod I, is a field if and only if I is a maximal ideal. This is a very famous result in ring theory. Let me make a comment, however, about the definition of maximal ideal. In the family of all ideals of R, which is ordered by set inclusion, R is in the family. R is an ideal of itself. So as far as maximal ideals are concerned, there's only one, namely R itself. So studying maximal ideals in this full family is trivial. There's nothing going on. So it's a waste of terminology, and therefore it has become customary to use the term maximal ideal to mean an ideal that's maximal in the poset of all proper ideals of R. And this is the same, by the way, convention we use in linear algebra and group theory as well. Maximal subgroup, maximal subspace, especially maximal subgroup. So it makes sense to use the term maximal as for the family of proper substructures of any algebraic structure. Well, the next thing that should be on our minds is, do maximal ideals even exist? Obviously an important question. But we can take a little bit broader view that yields quite an interesting result. And here it is in the picture. Suppose that I is a proper ideal of a commutative ring R, and that X is any non-empty subset of R that's disjoint from I. There's always one such set, because I is an ideal. It does not contain the multiplicative identity, so the set, the singleton set 1, is a set that's disjoint from I. Then we say that an ideal J, as pictured here, separates I from X if the ideal I is contained in J, but J is also disjoint from X. I think separate is the standard term. I don't believe I made it up, but as I think about this, isolate might have been a better word, that J isolates I from X. But separate, I believe, as I say, is the standard terminology. There are a whole collection of separation theorems in various branches of algebra, lattice theory, for example. And we're going to have another one here. We're going to talk about this more in ring theory as well. So, we'll denote the set of all ideals that separate I from X by this notation, ideals I semicolon not X. This is my notation. Again, I'm not aware of any standard notations, so I guess this is as reasonable as any. So this is the family of all ideals J that contain I but are disjoint from X. And this family is non-empty because I itself contains I and is disjoint from X. Now a simple application, if you don't mind me saying so, of Zorn's lemma, and you can review Zorn's lemma in the appendix, one of the appendices to this book, shows that this family has a maximal member, a maximal ideal. Because if we take a chain of ideals in the family, the union is an ideal. We discussed this a while ago. The union of ideals in general is not an ideal, but the union of a chain of ideals is an ideal. And this ideal contains I. In fact, all of these members contain I, so their union does. And it is disjoint from X because all of the members are disjoint from X. So it's a proper ideal of R that's disjoint from X. And so this union is in fact an upper bound for the chain. Belongs to this family, and it's an upper bound for the chain. So Zorn's lemma, which says that whenever every chain has an upper bound, there must be a maximal element, tells us that this family has a maximal element. And this is referred to as a maximal separating ideal for I and X. Now, let me caution, a maximal separating ideal for I and X is not necessarily a maximal ideal of the ring. We don't know what X is. It could be quite large. But if X is this singleton set containing the identity, then any maximal separating ideal containing I disjoint from this set. Well, they're all disjoint from this set. Ideals do not contain the identity. So this is in fact, this M here is in fact a maximal ideal among all proper ideals. It's a maximal ideal of the ring. So, summary, any commutative ring, I knew I was going to miss this, contains a maximal ideal. More generally, we have the following. For any proper ideal I of R, there is a maximal ideal containing I. That's where we set X equal to the singleton. For any proper ideal of I of R and any non-empty set X in R that is disjoint from I, there is a maximal separating ideal in this family. A couple of examples of maximal ideals. This ideal, generated by 2 and X, is maximal in the ring of integer polynomials. And I'm going to leave that for you to check. Another example, the units in the ring Zn, as we know, are the elements in Zn that are relatively prime to n. And we also know that Zn can be decomposed into a disjoint union of these three sets. Now, while Zn is not an integral domain, and so it can't be a principal ideal domain, it is still true that every ideal of Zn is principal, and we saw that in an earlier example. Let's take a look now at the maximal ideals of Zn. For any two elements A and B in Zn, we have A divides B if and only if the ideal generated by B is contained in the ideal generated by A. So if B is composite as an integer, then there'll be a prime P that divides B, and so the ideal generated by B will be contained in the ideal generated by P. Now this ideal could be all of Zn, but what we can say is that the maximal ideals are among the family of ideals of this form, where P is prime. Which ones are not equal to Zn? That's something we need to determine. If P does not divide N, then it is relatively prime to N, and so P is a unit, and so this ideal will be all of Zn, and therefore it's not maximal. Remember, maximal means maximal among the proper ideals. So the maximal ideals are now among the set of all ideals of this form generated by a prime, where the prime divides n, prime factors of n. So if n is prime, there are no maximal ideals. So suppose n is composite and P is a prime that does divide n. Then P is a non-unit, and so this ideal is proper. And if there is an ideal sitting between this ideal and Zn, then R is a non-unit, and it divides P in Zn, which isn't possible since P is prime. So this ideal generated by P is maximal. So in summary, the maximal ideals of Zn are precisely the ideals generated by primes that divide n. It's also important to note that a principal ideal may be generated by both a non-prime and a prime, so we have to be careful here. So in searching for maximal ideals, for example, in Z6, the ideal generated by 4 is the same as the ideal generated by 2. So this is a maximal ideal, even though 4 is not prime, but it's maximal because 2 is prime, and it divides 6. Okay. This example is a little testy. You might need to read it a couple times and then see if you can recreate it yourself. And I think that would be a useful exercise.